Okay, so I will give a 35 to 45-minute talk on RL, and then Meena Khan, who's I'm not sure she's around, but then she'll take over, and she'll talk about RL, more recent work, and then I think Yassine, which I have not seen him either, he will give a tutorial. Oh, there he is. Okay, great. He's going to give a talk on RLHF. Okay. Okay. So how many of you have taken a course or some lecture on RL? Also, lots. Not quite a few. So typically, if you open like a traditional textbook on machine learning, they don't have much on RL. Now things are changing. So I'll give the shortest path to something which is relevant these days, and see. So it'll be slightly unconventional. Let's see if I can sort of get it across. So first, I'll give a brief taxonomy of RL, and sort of machine learning, and then sort of try to situate RL in that taxonomy. Then basically then set up the reinforcement learning problem and give a couple of examples. Okay. Then there are two pathways to go to RL, and I'll explain what that is, and then we'll take one pathway, okay, which is easier for people who know what gradient descent is. Let's say. Then we'll do a mathematical formulation of reinforcement learning. Then we'll talk about the reinforced algorithm, which is the basis of much of the work that you see these days on RLHF and deep sea kind of work. And then we'll work through a toy example, and then we will, that's it, and then we'll have a small conclusion. Okay, so in the big picture, so the taxonomy of RL, there you can think of one class of problems, which is unsupervised learning, descriptive RL. So basically, in this setting, what you have is you have a data set X, and you essentially want to summarize it. You want to find clusters, you want to find patterns in it, okay. And the question you're trying to ask is basically what happened. You have data, you're just trying to figure out what is in the data. Okay? These are some of the hardest problems, by the way. For example, a lot of security problems, fraud detection, anomaly detection fall in this class of problems. Okay? And that's why they're so hard and almost intractable. Then, what you probably all know is the second class of problems, which is like prediction, supervised learning. In this setting, what you have is you have a pair. You just don't have an X, you have X and Y. Somebody gave you Y. And essentially, you're trying to infer a mapping from X to Y. That's pretty much all of deep learning. And your question here is, what will happen? So you give an X, what will happen? Which Y will happen? Okay. This is, this is slightly exaggeration, but I think this problem is pretty much solved now, right? Given X, Y pairs, you can figure a pretty good mapping between X and Y. And the third class of problems is what we'll be talking about is often called prescriptive learning or reinforcement learning. And here it's very different. So you're given X may not be data actually, it may be some abstract concept, and you're trying to learn some action to maximize a certain reward. Okay? And here it's not what happened or what will happen, it is how to make it happen. Okay? That's what you're really after. And basically, it ends up learning like we humans learn. It's like learning by trial and error. And a lot of the gaming stuff that you see, with the early motivations for RL, how the brain works. Some people speculate that's how we learn things by trial and error. So we'll be focusing on, this third track on reinforcement learning. Okay, so here is a typical RL setup. You may have seen this many times. Essentially, you have an agent, okay, and you have an environment. Okay? So the agent interacts with the environment, okay, and observes the environment through some abstract concept state, ST, at a given time t. Okay? Then, based on the state that the agent observes, the agent will take an action, AT. Okay? When the agent, trying to make things happen, takes an action, then the agent receives a reward, RT. Okay? Sometimes the reward is not immediate, it's later, sometimes it's immediate. Okay? And in the process of taking the action, the environment transitions to a new state, ST plus 1. Okay? And this process keeps going till you run out of time, you reach a terminal state, it can be infinitely long, forever. Okay? And then what your objective is to find a policy, it's called a policy, which is a mapping from state to action, okay? Which maximizes what's called the cumulative reward, not the immediate reward, but the sum of rewards. So summation of RT, t equals 1 to t, or sometimes also the discounted reward. You have a small gamma factor in front of the reward, and what that does is it basically, one thing is if RTs are bounded, then even if the sum is infinite, it'll stay bounded. But also sometimes, there's an economic interpretation to the gamma that, you value your immediate reward more than your future reward, though. But essentially, it's a hyperparameter, and typically people set it to like very high value, less than 1, so like 0.99 often. Okay, so here's a toy environment. Okay, let's just try to clarify some notation using a toy environment. So in this toy environment, you have two states, 1 and 2. You have 4 actions, A, B, C, and D. Okay. Now notice when I'm in state 1 and I take action A, I can go to state 2 with probability 0.75 and receive a reward of 2. Or I can come back to state 1 with probability 0.25 and receive a reward of 1. Okay? If I take action 2, right? If I'm in state 2 and I take action C, I come back to state 2 with probability 1 and I get a reward of 2, and so on and so forth. Okay? So you're interacting with the environment and you're generating these 4 tuples. Okay? The 4 tuples are state, action, reward, next state. State, action, reward, next state. Okay? So for example, state 1, take action A, get reward of 1.0, come back to 1, and so on and so forth. Okay? So remember, what we are after is, here we're just rolling out. Okay? But what we are after is a policy, which is a mapping from state to action. And this mapping is often denoted as pi A conditioned on S. So it's like a conditional probability. The function can also be deterministic. Okay? So for example, is this a valid policy? Pi 1 equals A, pi 1 equals B, and pi 2 equals D. Is that a valid policy? Why is it not valid?
Because for the same action, we are getting different.
Correct. It's not a function, right? It violates the basic definition of a function. If it's deterministic, it's not a valid policy. Okay? So for a finite state space S, cardinality S, and finite action space A, so how many distinct policies will you have if you're looking at deterministic policies? Is it S to the power of A or A to the power of S? You remember the basic function? I always get confused also. So many questions I ask is not, if I was on your side, I wouldn't be able to answer them either. So, okay, this is a homework exercise for you from basic discrete math 101. Okay, yes. Node 2, if you take action B
Yes.
or D, yeah.
If you take action B, you go to state 1 with probability 1, and you take the reward 1.
2. Reward 1, yes.
Okay.
Yeah.
And okay, thank you.
Yeah.
Got it. Thanks.
Okay. So remember, our goal is to find the optimal policy. Okay? And of course, as you can see, you have an exponentially many number of policies. Of course, if you have an infinite space and infinite action space, which is very common, say in robotics, right? Then, of course, you have infinitely many possibilities. It's infinitely many choices for the optimal policy. So what do we do when we have infinitely many possibilities, but we have only finite amount of data? We use function approximation. Okay? And so how do we do function approximation? We put some deep network and we learn from that, right? And then we can parameterize the deep network with theta. I'm using W here, right? So this is the only deep learning in this class, okay? So essentially, deep learning, function approximation, parameterized by W, rest, figure out, okay? Okay, so let's do some examples. So, how did DeepMind became famous? DeepMind became famous because they were able to solve the Go, AlphaGo, right? So in this case, you have a current state of the board, chess or Go, ST. You make a move, a chess or a stone. I know the rules of chess, but I don't know the rules of Go, so I'm assuming you have to collect these stones together and occupy space. You take an action AT, you may or may not get an immediate reward, RT, set it equals 0 or some small value. And then if you win the game, you have a terminal reward, you get a +1 or a -1 or something else, okay? Medical decision making, current state of the patient, ST, which you can measure from the parameters, right? Blood pressure, heart rate. The doctor makes a decision, AT, okay? They look at how the state of the patient changes, or the blood pressure improves, or whatever. There could be some reward to it, or could be delayed reward. And terminal reward could be if person lives or dies, right? That's the thing. That's the setup. Large language models. So you have a context, which is your state, ST. You make a next token prediction, AT, okay? What's the next state? Next state could be the concatenation of your context and the next token that you generate. That's a new state. And then the terminal state could be the end of sentence, right? And then, of course, what's the terminal reward? Well, it really depends upon what your objectives are. The DeepSeek paper has certain kinds of rewards. You may be more interested in safety. So if it's a safe output, then it's +1. If it's not safe, -1. You may not have a reward. People do preference learning. Yassine, I'm sure, will talk more about that, and infer a reward. Okay? So many problems that we deal with can be put in this RL framework. Okay. So when you take a course in RL, this is now how you start. The way I'm going to pursue. Because roughly there are two major schools of thought in RL. Okay? The first is the more traditional way and has deeper theory associated with it, which is formulated as a dynamic programming problem. Okay? Dynamic programming, you have something called a value function that captures the future cumulative rewards. Then you use the dynamic programming principle to characterize the value function, use a fixed point theorem then to come up with a way to finding that value function. And then you use some kind of a greedy algorithm to infer the policy from that value function. Okay? So basically what I have defined is all of control theory, all of optimal control theory, large chunk of econometrics, large chunk of logistics, supply chain. They follow this school of thought. Okay? But then there is another one which is more closer to what people in machine learning do, which is let's come up with some function approximation, use gradient descent, ascent kind of an algorithm, and directly find the policy. Okay? So in this lecture, we follow the policy gradient school. And of course, we have to sacrifice. There are many things that you'll not hear from me, in the sense I won't go into details, like Markov decision processes, Q-learning, value function, advantage function, which are extremely important. A few places I'll mention where these things come in. Okay, so what if RL was a supervised learning problem, right? So suppose we had data of the form S1, A1 star. That means in state 1, take optimal action, A1 star. In state 2, take optimal action, A2 star, and so on and so forth. Well, then we know what, we are very comfortable in this regime. We just set up it like a maximum likelihood estimation problem. Our goal is to learn pi w, A given S. We set up the maximum likelihood formulation. And because we are maximizing here, we use gradient ascent. So we update the weights, Wn plus 1, old weights plus alpha times the gradient, right? But as we said, we are not in this setting. We don't know the optimal action to take. We have suboptimal actions. We observe the world, we take some actions, we have no clue, but we get some reward. And based on that, we want to learn the optimal policy. So remember, it's very different from supervised learning. There we have the optimal labels, quote unquote. So you just have to learn the mapping. Here we don't have the optimal labels, right? So as I mentioned earlier, data is in the form of these episodes, trajectory episodes. They're sequential, S1, A1, R1, S2, S2, A2, R2, S2, okay? We don't have access to optimal actions, okay? But just action plus a weak reward signal. This is the key difference between RL and SL, okay? And how do we extract an optimal policy from non-optimal signals? So it's a much harder problem in some sense. It's closer to unsupervised learning to a certain, if you think about it. So let's set up the mathematical formulation of RL. Because if going the policy gradient kind of school, we follow that approach. So we define, let's define a trajectory S bar, which here we just have tuples S1, A1, decouple the rewards from here for a moment, okay? And let's define this P, capital P, parameterized by W, S bar, which is the probability of selecting a trajectory S bar when using policy pi w, okay? So we are generating a trajectory following a policy pi w. Remember, our goal is to find the optimal policy, right? So it's highly coupled. Data generation and recovering a policy is highly coupled here, as opposed to supervised learning, where they are independent, or decoupled rather. Let R of S, which is capital R of S, be the total reward associated with its trajectory, okay? RS, as we said, is gamma to the gamma T RT, sum over T, okay? And so the learning problem that we have is essentially finding argmax or max of the expectation of R of S bar, where the expectation is over the distribution PW, okay? So again, notice the difference between supervised learning and reinforcement learning. PW comes from the policy PyW, as opposed to supervised learning where data is given to you, right? The data is fixed but unknown. The distribution is fixed but unknown. Okay? So that's what I was saying. The trajectory distribution is unknown, okay, and not fixed. Okay? In contrast, in supervised learning, data distribution is unknown but fixed. Okay? This is a key difference between RL and SL. We don't have access to the target optimal policy. We don't have the optimal labels. Okay? And this leads to two unique things about RL that you may have heard. One is called exploration exploitation. Okay? Should we settle for the distribution that we currently have when we are trying to solve the problem? It's called exploitation. Or should we try to make some effort to have better distributions? That's called exploration. So a common example is you come to Doha, you check out some restaurants, you like a restaurant. Should you just stick to that restaurant and go every day to eat there, or you try and explore and try to find some other restaurants with the hope that you'll get something better? And the other thing is credit assignment, okay? What is the impact of an intermediate action on the final return? Okay? And how do we capture, quantify credit assignment? If you, in the AlphaGo, they were saying, okay, when they were playing, AlphaGo was playing with the world champion, there was one move number, I've forgotten, 18 or 13, which people didn't understand. Or move 37, and that turned out to be the key move. So how do we give credit to, how do we know that that was the key move? How do we quantify the credit to that move? And this problem is, these two characteristics are unique to reinforcement learning. Okay, so here's the most important theorem in policy gradient reinforcement learning, and we'll use it to design an algorithm, okay? So let's denote by the gradient, the nabla of hat S bar as R of S bar. Remember, R was a return, sum of cumulative rewards, times the sum of I equals 1 to t, gradient with respect to W of log of pi ATST. Remember what was pi? Pi was the? Pi is the policy. We take, it's like a distribution. We take the log of the distribution, and we take the sum over all the length of the trajectory, and then we just multiply by the reward, the return. Okay? The sum of the rewards is called the return. Okay? Then the theorem says that the expectation, okay, over PW of the nabla hat of S bar, right, is equal to the gradient of the expectation of R of S bar. So now let's stare at this for, it's very abstract. Let's stare at this for a few seconds. This is an equality. The right-hand side, of course, we can't compute, right? It's over the expectation of PW, right? The left-hand side is an estimator, right? Okay, so we can get our hands on it. We can generate a trajectory, okay, and we can actually calculate gradient hat of S bar, okay? And basically what this is saying in expectation, they are the same, which is very nice. But the most important takeaway is, which initially turns out to be very surprising, is that there are no gradients attached to R of S bar, okay? So what this really means is you can take R to be anything you want, okay? For example, You can learn R from, R can be rule-based. In the DeepSeek paper, RL, they have a rule-based way of finding rewards. You can infer a reward from some other data set, right? So you can essentially have full freedom to select R, and because you're not differentiating it, you have this luxury, and this turns out to be the key thing, okay? Which also means that you have sometimes you convert. It's almost like a zero-order estimator, so you have some issues with convergence. Okay, and the second thing is because of it's an unbiased estimator, the left-hand side of the right-hand side in some sense, but it tends to have high variance. Why does it have high variance? Because you're taking the sum, right, intuitively. So sum of the variance of the sum is like the sum of the variance. So the variance explodes, accumulates, right? So a lot of effort is made to actually reduce the variance. So they can reduce the variance by doing some subtraction of RS, by normalizing RS, okay? By subtracting what's called the baseline. And that's where the connections between the other school of RL, which is the value function, and Q learning comes in, okay? So we'll not get into that. But reducing the variance is a big, big problem in policy gradient. They take a long time. That's why, the world's leading experts like Jan LeCun and other people are a little bit pessimistic about RL because they think the sample complexity of RL is too high for it to be practical. But now it seems like things are steering towards more towards RL. Okay? So we can use RL to basically define the key algorithm for reinforcement learning, which is called the reinforce algorithm, which is, all the papers that you read on RL in LLM essentially are variations of this algorithm. So I want to sort of go through, basically derive the algorithm for you. So then if you read a paper, then you know exactly what's going on behind the scenes. So basically what happens is you initialize your policy. Remember, policy is pi by some parameter w arbitrarily, right? But when you're in the LLM world, it doesn't have to be arbitrarily. It can be your SFT policy, okay? So then you want to generate M episodes. Remember, you don't have any data. Now you start interacting with the environment, and the episode is one trajectory. So you say, okay, I'm going to generate M episodes, and the episode is S0, A0, R0, S1, and so on and so forth. And now what I'm going to do is I'm going to learn a policy from the, update my policy from the generated episode. So I go into another loop for t equals 0 to t minus 1. I define this return function. Basically, I'm at time t. I just calculate the discounted return from time t. Okay? This is, by the way, crucial for the credit assignment problem to have your return like this. Okay? And then I just update my weights like my standard thing that you've learned in this course, except instead of having a minus sign, you have a plus sign. Why? Why do you have a plus sign instead of minus sign? Because you're maximizing, right? So, so instead of minimizing, okay? And that's it. So this is the reinforce algorithm, which is very simple, and the basis behind all this big interest in reinforcement learning, and it's been there for many years. Okay, you may have heard of algorithms like PPO. All these are based on the reinforce algorithm. Okay, so let's do a detailed, like a small example, and then we'll stop. So imagine you have the grid world, which is like a, it's a hello world of reinforcement learning. So you have a 2x2 grid, and essentially what you want to do is the agent can take 4 actions. Agent can move left, right, up or down, okay? And based on how the agent moves, they get a certain reward. Moving into the bottom right-hand corner, 1, 1 gives you a reward of 10. Otherwise, moving into 0, 0 gives you a reward of -10. Otherwise, you get a reward of 0, okay? And 0, 0 and 1, 1 are the terminal states. Okay, so we have a policy pi w, which is, as we discussed, is parameterized by w. Behind the scenes, it's a big, deep network, okay? And the policy can be stochastic. So how do we take logics and make them probability? We use this softmax thing, right? And then the agent starts in a state 1, 0 and takes an action right, okay? And because it went to 1, 1 from 1, 0, it gets a reward of 10, okay? And then, very simple, you have your weights. You get your cumulative, you only have 1 step, so you get a cumulative return of, there's only 1 reward as the return, so you get 10. And then when you take the gradient, you get 1 minus pi w. Okay. Now before backprop was, now of course it's very easy. You just go policy x dot backprop quotes and it does it for you. But 10 years ago, you had to do it by hand. So you may have forgotten what the gradient of a softmax is. So again, some exercise for you to figure out why do we get this thing, okay? So 1 A naught is the 1 hot encoding vector. And anyway, so you can analyze this expression in detail, and what you basically get is when you take, you move your direction to the right, for that action, the weights go up. For the other actions, the weight go down, and they are multiplied by your return. So it's very intuitive. I think it's a good exercise to take some simple example and work it using on a paper and a pencil, because then you get the intuition. But if you just type, like I said, policy.backward, you don't get intuition about really what's going on behind the scenes, okay? So that's it. So essentially, RL is a broad class of algorithms and for learning sequential decisions, okay? It's as old as AI, but it's on this sort of sideline sometimes. So all reasoning paradigms in our LLMs these days, like, of course, DeepSeek R1, and most likely the O1 OpenAI model, the O models, use RL in conjunction with what these are being called chain of thought examples, okay? But the underlying principle is actually very, very simple, and hopefully you will be able to get from here. So as I mentioned, all popular algorithms are based on this. And the key thing is we are using suboptimal data to extract an optimal policy, which, if you think about it, is very, very, almost seems impossible. But in some cases you can, you'll probably never achieve the so-called optimal policy, but close to an optimal or good enough. And yeah, so that's it. Thank you.